Hello friend, welcome to the abstract algebra class. It is class 34. Here we will prove a theorem about coset groups. Theorem H is any subgroup of a group G with respect to multiplication, and A belongs to G. And A belongs to G, then A belongs to H if and only if H equal to H HA. Right coset, left coset equal to the subgroup equal to the right coset. Proof. Let G with respect to multiplication be a group and H be any subgroup of G. Let A belongs to G. A belongs to G. We have to prove that A belongs to H. A belongs to H. A belongs to H if and only if H equal to H equal to HA. Suppose first we want to suppose the right side and prove the left side. Suppose AH equal to H equal to HA, then we have to prove that A belongs to H. A belongs to H, left side. Let E belongs to G be the identity element. Then E belongs to H because H is subgroup of G. Every subgroup of a group has at least an identity element. Therefore, when E be an identity element in G, then E is an identity element in H because H is subgroup of G. E belongs to H. E belongs to H, and here given A belongs to G, it implies A into E belongs to AH. Why? Because H is subgroup of G. E belongs to H and A belongs to G. This implies as a coset, as a definition of coset, A into E belongs to left coset. We define left coset as like this: A into H equal to AH such that H belongs to H. Also, we know that A into H equal to A into E such that E belongs to H. Here, A into E belongs to AH. A into E belongs to AH. This implies A into E, it will become A belongs to left coset. Left coset, we have left coset equal to H. Left coset equal to H. This implies A belongs to H. A according to the definition of left coset, A into E belongs to A into H, belongs to left coset. This implies A belongs to left coset equal to H. This implies A belongs to H. Here, it is the left side. We assume which right side is true. That is AH equal to H equal to HA. Then we prove that A belongs to H. Here, it is the result. Converse of the theorem. First, we prove that we assume that the left side is true. Then we prove the right side. Suppose A belongs to H. Here, A belongs to H. We have to prove that right side. Right side is left coset equal to H equal to right coset. Let H belongs to H. H is an arbitrary element belongs to H. Then H equal to H into E. E is identity element. Every element can be written as H into that element multiplied by identity element. It is equal to A inverse into A inverse. Every element identity element, every identity element, according to the definition of identity element, A to the power minus 1 into A. Therefore, instead of E, we put it A inverse into A. By associative axiom, we can write it is equal to H into A to the power minus 1 into A. It is equal to H into A inverse. It will, we put it H dash into A. H dash equal to H into A inverse. It is the value of H dash. Therefore, H equal to H dash into A belongs to HA. It is right coset. We define right coset. Any element into any element of G, it is belongs to the right coset. Therefore, H equal to H dash into A belongs to right coset. This implies when H belongs to H belongs to H. This implies H belongs to H. Here, H equal to H dash into A belongs to H A. It means H belongs to H, belongs to subset of H, a subgroup of H, implies H belongs to right coset. Therefore, H is subset of right coset. H is subset of right coset. We call relation 1. Since HA belongs to HA, we have A belongs to G, H belongs to H. It is the definition of right coset. H into A belongs to HA. We have A is an arbitrary element belongs to G, also H is an arbitrary element belongs to H. Since A belongs to H, from here we say A belongs to H belongs to H, and H is a subgroup of G. H is a subgroup of G. By closure axiom, we can write the product of these two elements also belongs to H. HA belongs to HA. HA belongs to HA. Implies HA belongs to H. Implies HA belongs to H. Therefore, HA is a subset of H. Is a subset of H. It is relation 2. From 1 and 2, from equation 1 and 2, we get HA, when HA subset of H is subset of HA, we get HA equal to H. Similarly, we can prove that HA left coset equal to H. Left coset equal to H. We prove that right coset equal to H. Similarly, we can prove that left coset also equal to H. From these two relations, we can conclude that a left coset equal to subset H equal to right coset. Hence, A belongs to H. Hence, A belongs to H. If and only if AH here, AH equal to H equal to HA. It was the proof of this theorem. Thank you.